All right, everyone, it's that time, 11 a.m. here on the West Coast. We are live today from LPKF Laser Electronics Studios in Portland, Oregon. And today we are going to be presenting our newest SMT webinar, Stencil Aperture Size and its Impact on the Printing Process. Today's presentation is based off a white paper written by Anna Osterhoff of Eastwood Consulting and Stefan Schmidt, president of LPKF North America. My name is Shane. I'm in the marketing department here in Portland, and joining me today is Mr. Osterhoff himself. Anna, he's an expert in the stencil manufacturing industry. He served many years as an engineering manager at Tektronix, and he also founded the company A-Laser. These days, he spends his time serving as an independent consultant on many SMT stencil matters. If you have any questions throughout today's webinar, feel free to submit them via the Go To Questions panel as seen on your screen. Or we can do something a little different. You can submit them via Twitter. You can do this by tweeting to the LPKF Twitter account, which is @LPKF_USA, or you can tweet your question with the hashtag #LPKF. Now, we just have a two-man booth today, so we'll likely be answering all questions at the end of the presentation. But if I happen to see anything along the way that's relevant at the time, we'll pick it up then. So now, if you paid attention to the webinar description on the registration page, you might already know the answer to this, but we're going to get started with a little quiz. What percentage of board assembly problems stem from solder paste printing? This is a pretty big issue, so I'm going to go ahead and launch this little quiz/poll, and we'll see what you guys think. And we'll go ahead and give it about a minute, and then we'll see what you have to say. All right, we'll go ahead and close it now. Looks like you can see on your screen, majority of the people selected 75 to 90%. Well, if you answered actually choice D, then you're correct. The most commonly number reported for board assembly problems stemming from solder paste printing is 60 to 75%. So let's say we know that we have this 60 to 75% of problems. Well, how do you not get them? Well, the thing that you need more than anything else is you need a stencil that gives you the right amount of paste in the right location. So if we're talking about the right location, we actually already gave a webinar on that. It was called How Stencil Manufacturing Methods Impact Precision and Accuracy. You can find this on the LPKF USA website if you're interested. But today, we're going to be sticking more to the right amount of paste part of it. So, Anna, why don't you tell me a little bit about what right amount of paste really means?
Well, that means you need the correct aperture sizes and you need the correct material thickness. Together they determine the aperture volume. And of course, also, once you have the right volume in the stencil, it has to be released properly to the board. So that gets you to a term called area ratio, which is the ratio between the aperture area and the wall area. The area ratio gives you an indicator on whether or not you will get sufficient paste release. And the typical number for that has been 0.66. So if your area ratio is above 0.66, you're likely to get the right amount of paste. Why do we do this? Why do we use this number? The wall area is the item that tries to keep the paste inside the aperture, and the pad area that you can see through the opening essentially sucks the paste out of the pad. So you need enough pad area showing to get paste release. Now, today there are ways to go beyond that 0.66 number, and we'll come back to that later. We have seen numbers as good as 0.45 and even better than that.
And Anna, the 0.66 for the area ratio, that's not necessarily like a rule. Like you don't have to be at 0.66. It's more of a rule of thumb, right?
That's correct. So it doesn't mean that at 0.65 you don't get paste release and at 0.67 you do. It's a rule of thumb only. It's not a standard.
So it's more of a, if you get 0.66, call it good sort of thing.
Right.
Sweet. So now in relation to area ratio, how do we assure that we're getting the right amount? Well, we've got to make sure we have the correct aperture size, correct material thickness, as we mentioned, and good paste volume. So what influences that? Well, it's the manufacturing process. Now, we have a little thing we like to call the 4 M's of manufacturing. Many of you may be familiar with this. So, Anna, why don't you walk through the 4 M's and explain what they are?
The first one I listed is methods. And how is the stencil manufactured? Are you using a chisel, chipmunks, a laser, or electroforming? The other one is the quality of the equipment you're using. Essentially, is your chisel sharp? Do you get a well-defined, correct aperture? And then there's the properties of the materials that you're using. For electroforming, typically it's nickel. For most laser cut stencils, it's stainless steel, or you can even use Kapton. And then the last one is the capability of the people involved in the manufacturing process, the manpower. So are they setting up the machine correctly? Are they choosing the right metal from the bins of metal, etc.? So missing something in any of these areas will give you a lower quality stencil that may not give you consistent paste release and the amount of paste that you really need on your pads.
So what we wanted to do in order to be able to test to see how good area ratio you could get, we wanted to test the manufacturing process. So how do we do this, Anna? We created a test, and will you just explain the test?
It's relatively simple. We have a large stencil, ordered it from a number of vendors, just like any other customer would do. No special instructions, no hint of the purpose for which the stencil was going to be used. So it was ordered as a 125 micron thick stencil, 5 mil, and the aperture area for this stencil was not always better than 0.7.
So if it's ordered to be 125 microns and the area ratio is supposed to be 0.7 or better, the question of course becomes, did we get that aperture size as we desired? Did we get the proper thickness? Well, this is where we get into the 4 M's and how they would influence just how accurate the stencil aperture sizes would be. So, Anna, we mentioned on the last slide that out of the 16 stencils, we had electroformed and laser cut. Can you walk us through the manufacturing processes of both and explain why the inherent nature of those processes can affect stencil quality?
Sure. Let's start with electroforming. The customer that wants the stencil sends data, and it has to be processed to get ready for the manufacturing process that is being used. In the electroforming process, first you do is produce a film so that you can transfer this image to the mandrel. Both of these steps are have to be controlled well because they will impact the size of the aperture. After that, the mandrel is placed in a chemical bath and a nickel layer is grown on this mandrel, except where the little islands are that are going to become the apertures in the stencil. This particular step controls how thick the metal is going to be, so proper control is needed at that point. Once the metal is thick enough, the mandrel is removed from the chemical bath, the nickel layer is peeled off the mandrel, mounted in a stencil. The mounting can cause another problem because now you're exerting tension on the metal layer, which may stretch the metal to some degree, which in turn will impact aperture location. This is especially a problem when you have very large stencils. The other process, or taking a look at an electroformed stencil, you can see here a crosscut of the stencil. The aperture walls are indicated, and you can see the walls look rather smooth. There are some striations there, but they are in line with the paste release, so they don't form a problem. The process takes chemicals, and personally I have never liked chemical processes, so I stayed away from that when I was running a laser. It requires tight process control. You have to meet all the rules and regulations when it comes to chemical processes and chemicals. You have to be able to get the proper chemicals and store them, and the biggest question is always, how do you get rid of the waste? So from my point of view, I didn't like electroforming. From a performance point of view, we have been able to always been very close to the performance that you can expect from an electroform stencil. And additionally, there are processes called electro-polishing or can polishing, and I have found that those don't make a significant improvement or improvement at all when it comes to paste release. So chemically, it's out. Taking a look at the laser cutting process, it starts in a similar fashion. You get the data from the person who needs the stencil. It gets processed to be prepared for action on the laser system. The laser system is used to cut all the apertures in the metal sheet, and when that is finished, the metal sheet is mounted in a frame. The nice thing of this process is that you can skip a step by mounting the metal sheet in the frame before you start cutting. The advantage of that is that the turnaround time from receiving data to shipping a stencil is shorter, and it also improves the precision of the location of the apertures because the tension on the metal does not change from raw metal to finished stencil. When you look at a cross-section or the aperture walls in the stencil, you can see here a picture. There's still some striations due to the flow of the liquid metal that was blown away by the airflow or oxygen flow. So the laser is actually pulsing, so little high energy pulses are used to cut a little bit away, to nibble away the metal layer. The curve that is being made by the laser is very narrow. It's the width of the laser beam, and typically that runs between 20 and 40 micrometers. So the curve is much smaller than the aperture width, and when you're done with a single aperture, there's a piece of metal in the middle that gets blown away and disappears in the waste stream. This particular picture has a slightly higher magnification than the previous one, so the striations do show up clearly, but because the top to bottom of the striations is so shallow that the impact on paste release is minimal. To talk a little bit more about the laser, to get an idea of the pulsing problem, the particular top left corner of this image shows the edge of a postage stamp, and I use this to clarify what the laser does. If you move the metal too fast under the laser beam, the pulses become separated from each other and the metal wouldn't be dropping out of the intended aperture. So you have to either increase the pulse rate of the laser or decrease the speed of movement. And when you look at the top right corner, that looks like a piece of paper that was like a form that is laser cut, and the pulses are much closer together, which means the paper will be separated from its original sheet. And then the bottom part is a piece of paper cut with a knife, and that's equivalent to today's modern lasers, which are diode pumped, have a much higher frequency, so the pulses are close together, and even because of that, you can move the metal faster, so you get faster turnaround time in the process. This particular image shows you an aperture that was cut on a fiber laser pumped by diodes. You get a smoother walls, as I already mentioned. And the biggest benefit of this particular type of laser is that it uses much less incoming power. When you compare a fiber laser system with the older lamp pumped lasers, the original ones were drawing 5 kilowatts or more power to run the system. So it meant 3-phase 480 volts to power the system. The newer systems you can plug in the wall because the power consumption is less than a kilowatt.
So speaking of the differences between like the lamp pump and the diode pump, that brings us to our second of the 4 M's. So when it comes to machines, there's a lot of different machines out there that you can choose. You can see some up here on the screen. So Anna, could you just explain a bit about the variability that exists on the machines out there that are actually cutting the stencils?
The most visible difference when you look at older machines versus newer machines is the amount of mass that you're moving around. And the more mass you have to move, the harder it becomes to move it in a straight line, and when you have a rectangular aperture, move it around the corner without overshoot or undershoot in those corners. So when you look at the image, the top right laser is one of the older versions, and that upper table that holds the metal sheet rides on top of the Y movement system. So that means the whole X movement system has to be transported for a Y movement. So there's a lot of mass. In the bottom left image, that particular system, you still have the Y movement, but actually the laser beam is moved in the X direction, so there is much less mass to transport. And then in the 2 newer machines, the mass has been reduced further, and those are equipped with fiber lasers, diode pumped fiber lasers, so they have additional advantages in performance. So as far as the equipment and the machines go, in the electroforming process, the first 2 steps that I mentioned impact the aperture size. That was the photo imaging of the mandrel and the preparation of the photo. And the third impact there was the chemical process, which had to be tightly controlled. In a laser system, it's the system's use and maintenance that impact the aperture size precision. And for both of those systems, you have to make sure that the data is prepared correctly, because without the correct data, you won't get a good stencil.
And later we'll actually talk a little bit more about data prep and how that can affect the whole accuracy of the stencil aperture size. But for now, let's get back to our test with the 16 stencils. Anna, up here on the screen we can see I have a screen cap of the stencils. Why don't you describe the stencils to us?
Oh, this particular stencil was for a very large board, so it's a stencil that was actually initially made to go into production. The stencil size, the image size on the stencil, is about 500 by 350 millimeters, so it's a very large stencil. in a way that's uncommon, but at the same time, a lot of small stencil for small boards come as a palette or come as a large pattern for multiple boards. So the 500 by 350 millimeter is not uncommon. This particular stencil also has 21,000 apertures, a very large number of apertures, which was important for our test, so we could get a large sample size for from our measurement system.
So Anna, once you ordered the stencils and got them back, how did you check to see if the aperture sizes for all those 21,000 apertures on each stencil, how did you know if the aperture sizes were as desired?
Well, in my case, that was easy. There's a system that I'm depicting here. It has a glass plate on the table that moves underneath the light bar, which is on top. And in the bottom of this machine are a number of line cameras. So as the stencil moves below the light shines through the apertures, gets captured by the cameras, and the computer will then take that information and develop a picture, and at the same time also calculate the size of each aperture and the location of each aperture. Once I have that size information, I can move it into an Excel spreadsheet and develop a distribution graph of that data. So take a look at the captured information. When you look at number 1 in this bottom corner, it shows the blue information, the blue series of pixels actually, and the computer will calculate the number of pixels and determine from that what the size of that aperture is. It also will calculate the centroid of the aperture and compare it to the information from the original stencil. When the computer looks at that data, and you look at number 2 there, you can see there are a number of pixels missing in the aperture. That in turn will impact the calculation of aperture size and of the calculation of the centroid. But I can visually inspect the data before finally using that in my spreadsheet and exclude specific apertures that have debris in the data field till I get to the apertures that are clean enough to include. Another item in the picture, number 3, you can see the blue area, which is the actual aperture, and then the red line, which is the intended location of the aperture. So that shows me that the aperture is, the centroid of the aperture is away from the centroid of the intended location. So that gives me a lot of information from this measurement system. And the measurement system for this large aperture takes only about 5 minutes to get all that data. So it's a useful part in the production process. Once I move the data into the spreadsheet, I can take the raw data, which is the inner curve, and add an appropriate bell curve for that kind of data. I also can determine what the specification limits are that I want to use. And for this particular test, I chose plus or minus 10%. So I want all apertures to be better than less than 10% off from their intended size. Having that information, I can then calculate CP, which is the ratio of the spec width over the distribution width, and the CPK, which is essentially the ratio of half the spec width over the worst half of the distribution. So now on this graph I have combined all the raw data from all 16 stencils, and you can already see significant issues. The best stencil is that dark yellow one, almost orange one, It's a very narrow distribution, which also means it gives you a very tall distribution. And of course, that's the kind of stencil that you would like to see. On the other hand, when you look at the far left side, you see apertures that are way outside the distribution. So the first one has a very high desirable CPK, but the ones that are shifted to the left have low CPK. To take a look at the CP for all these stencils, obviously the first one in this graph stands out. It is that one that I mentioned first. It is way within the distribution in the spec band, so it has a very high CPK. Going to the other end, you see that almost all these stencils, their CP is not that bad. They are all one or better. So the distribution in size is not undesirable. What makes a distribution in size? Well, I talked about the mass that had to be moved in order to get X and Y movement. And there is also the stability of the beam. The width of the beam determines the curve that is being cut in the metal to ultimately form an aperture. If the beam varies in size, the outside line, the outside location of the aperture wall is going to vary in width, and you get this wiggly line that is shown in the left image. In the right image, you see a very straight wall and excellent corners in the rectangle, so that would indicate a stable beam and stable movement system, which is what you need for a good stencil. To take a look at the CPK for all these stencils, again, the best stencil is the one on the left. It has a very high CPK, which is to be expected because visually you could already see that all the data was within the spec band. On the right-hand side, you see apertures or stencils that have a CPK that is really bad. It is in a negative range, and that's because almost all the data is outside the spec band. So what could cause that particular kind of a problem? Well, the number one is poor data prep. Using instructions wrong, using the wrong beam diameter in the system, in the calculation of the cutting path. So the stability of the beam is important, and you have to take into account what the size of the beam is. The laser system is like a milling machine, and if you don't know the size of the bit in your milling machine, you don't know what size openings you're going to get. To take a look at various machines, here's a comparison between two systems. One is an older system, and on the right-hand side is the newest system, the most modern one. And I can also say that that particular one was used by an operator who knew exactly what it was doing and how he could get the best performance out of the machine. So you see a very high CP and a very high CPK for the good machine, a low CPK and a low CP and a negative CPK for the older machine.
Exactly, and that ties into what we were talking about with older systems versus newer systems. There's difference in types of laser, there's difference in movement systems, and at each location which you order your stencils from, there could be difference in preparation as well, the manpower element of the 4Ms. But we did just mention data prep a minute ago. You said that's the number one reason that could cause such a huge variation. So why don't you explain that a little bit about data prep, our third M that's part of Manpower.
I mentioned the laser system is like a milling machine. So when you have a machine with a specified beam size of, let's say, 40 micron, if you calculate your cutting path on with a beam with an expectation of the beam being smaller, then all the apertures will be smaller. So the inverse, of course, is also true. So what it means is that the operator of the laser system has to regularly check what the beam size is. One of the things about the laser beam is that it's not necessarily the same from week to week or sometimes even day to day. So verifying machine quality is a necessary step in the operation of the system. So you have to know the quality and the specifics of your machine and make sure that the data preparation has taken that into account. The machine has to be maintained properly and set up properly. The laser beam is formed through a number of optic systems, and if those optic systems are not clean and adjusted correctly, you don't get the beam size that you want, you don't get the energy distribution that you want in your beam. And then the last thing is, you have to, when you set up the machine, you have to put the right material in it. So if the operator chooses the wrong material from the bin, from the selection of materials that he has available, you don't get the thickness that you want. This particular graph shows two machines, or actually it shows the same type and brand machine, but it's operated by a different group of people. And so now you can see that that particular aspect, manpower, can impact the quality of your stencil.
So Anna, if you don't mind, I noticed back on our big chart with all the distribution for the different ones, Stencil FL actually had a double hump, and some watching today might have seen that. So how did this double hump happen?
Well, first of all, it's not a bad stencil, even though it has that double hump in the distribution. The CP is 1.1, CPK is 0.6, so really most of the apertures are within the spec band. It's quite usable stencil. To take another look at that, the possible reason for this double hump may be that the operator changed the power while he was cutting this stencil. What he could have done is cut all the smallest apertures with a different power and speed setting than the larger apertures. And the reasoning would be larger apertures you can cut faster, so your aperture wall may not be quite as smooth as possible, but because they are large apertures, they have a high area ratio, so paste release is relatively easy. For the smallest apertures, you want to make sure that you have the best aperture wall possible, so you run it at a different cutting speed. With the higher cutting speed, you may also have to choose a little bit more power, and that little power may also increase the effective beam diameter of the laser beam. And that would, of course, result in a different aperture size, or at least a percentage aperture size. And that would explain the two humps.
So all in all, it's a pretty clever move by the operator to try to save some time. And really, kind of this whole section, it really exemplifies the old quote we like to talk about, which is, I can make a bad stencil on any laser and a good stencil only on some lasers. So you could have the greatest machine in the world, but if you're not operating it correctly, well, you see what could happen. But moving on from Manpower, we get to the last of our 4 M's, materials. So Anna, go ahead and talk about the choice of materials, how that plays a role into apertures, and specifically talk about this in relation to how certain materials have changed the game when it comes to an acceptable area ratio number.
Going back for a moment to the graph that showed all the distributions of the stencils, we want the distribution to be less than 10%. So some graphs are narrow and high, some are wide and outside the spec band. So when you look at that group, those two that are outside the spec band, and look at the leftmost leg of those graphs, you see that the apertures are 30% or more smaller than they're supposed to be. Most of the apertures are only 20 or 25% too small, but those ones that are really 30% too small are going to cause problems. The area ratio is also 30% lower, which means we expected an area ratio of 0.7 or better, but for these apertures we get an area ratio of 0.49.
So when you get that reduction in area ratio, that likely means you're going to have to start paying up for better materials, right?
Yep. A paper that was published by Bob Dervas compared various various metals that were used on lasers, and it compared a number of stencils. The typical area ratio that I mentioned in the beginning that we want to exceed is 0.66. So the yellow line, the yellow vertical line, represents this 0.66. So when you look at the light blue bottom line there, where it crosses the horizontal line, that's the point where you say, okay, 0.66 gives you enough paste release. So that horizontal line is the limit for paste release. All the other stencils that were being tested in this particular test gave better paste release. And the best one, which is that red line, it intersects that line, that's paste release line, at the vertical purple line. And that particular line indicates an area ratio of 0.5. So the stencils that we just looked at and talked about, the two that had the worst distribution and therefore an area ratio of 0.5 or slightly less, the only way to make those stencils work is to go to this fine-grained stainless steel that allows you a better paste release. So these stencils that were being tested, the ones that weren't included yet at that time was nanocoating. And there is some information that says nanocoating gives you a paste release, acceptable paste release, even at 0.45 or less. So that means the next graph would be above the red one and cut the horizontal line almost off the graph. But I have not done any test on nanocoated materials yet.
So Anna, we've covered methods and how electroforming versus types of laser cutting can influence the manufacturing process of the stencil and getting to an acceptable area ratio. We've talked about the different machines, the differences in movement. We've talked about manpower, how data prep and proper power settings can all influence it. And we've also talked about the choice of materials. So what's the takeaway from all this information?
Well, really what it means is if you're in need of a stencil and you go to Mikey down the street, you don't know how he does it and what he does, and once you get the stencil, it may not work. So in order to get good stencils, you have to know the supplier's methods. Is he using the best methods to prepare the data, the best methods to run the machines, and does it fit does those methods fit with what you need? Are you using very small apertures? Are you using, do you need to use thick metal because you have a number of apertures that are large and components that need a lot of paste? So you have to make sure that the methods, machines, manpower, and the materials that the manufacturer is using are all as good as they can be for what you need. So you have to visit your stencil manufacturer.
And I think that's it. So it's in a way, it's a call to action. You've got to make sure that your supplier's process and methods work and that they match your data. So with that, we've reached the conclusion. I wanted to thank everyone for attending today, this Thursday, December 6th. I wanted to mention really quick, if you had any more questions about stencils, you can go ahead and contact us. The phone number, that's our line here at LPKF, or you can contact us, sales at LPKFUSA.com. But if you want information specifically to SMT stencils, we have a portion of our website. It's lpkfusa.com/SMT stencil. And that's where you can find, we have 3 white papers up there. We'll have this webinar beginning tomorrow after we get it uploaded on the website. And we also have, in the beginning I mentioned a webinar about stencil positional accuracy of apertures. And we have that webinar up there as well. But now we'll go ahead and have questions. So we have a couple questions already, but we're going to go ahead and pause for a moment. If you have any questions about any of the manufacturing processes we've talked about, or any questions about the test, go ahead and submit them now, and we'll check up in just a minute. Okay, so we have some questions here. We have one question talking, I think, a little bit about how the laser works. It's, does the laser go all the way through and then do the pulse cut? Anna.
Oh, how do I explain that? When you start cutting an aperture in the laser, think of it this way. The first pulse that you put, the liquid metal that you're trying to blow away goes over the top of the stencil. So when you start generating an aperture, you start from actually standing still till the first few pulses cut through the metal. Once you're through the metal, you start moving, and now each pulse nibbles away a little bit more of the next part of the metal. So the very first pulse almost goes through, not necessarily, but the second one certainly does. So it really depends on the energy density of the beam, how fast you're going through that first step.
Gotcha. That's a very, very astute explanation, Anna. So we have another question. This comes from Michael. He says, do stencil manufacturers commonly use the machine you showed to verify the stencil prior to shipment? And I believe what he's referring to is the AOI equipment. So, Anna, do they normally use to make sure that your stencil is just A-OK right before they send it out?
There are a few of those machines being used. The problem with that particular machine was it was rather expensive. So it did not gain wide usage in the field of stencil manufacturing. There are a number of alternatives available, but the alternatives are not as fast, and it takes longer to test a complete stencil.
So usually your stencils, then, they're not getting checked before they get back to you, right?
Most of the time they're not getting checked to that amount of detail.
Gotcha. I've got a couple questions about getting a copy of the webinar to those who maybe missed the beginning or had some other interference. So what we're going to do is probably tomorrow you'll receive an email with a copy of the slides and a recording of the presentation, which you can then share with whoever you want. I'm going to go ahead and give just a minute or two for questions. We still have some time. So I'll pause for just 30 seconds to a minute more, and if you have any more questions, get them in now. All right, well, it looks like we're not getting any more questions today. So if you do have any further questions, feel free to contact us any of the ways we mentioned, either emailing us or calling us, and we'll get your questions taken care of. In the meantime, I hope you all have a good upcoming weekend and a good holiday season. Thanks, everyone.